when you're constructing the unit circle, the one thing you don't want to ever lose sight of is the fact that it's a circle with radius of 1 unit. All right. So that's telling us that at any point along the circumference, we're looking at a distance of 1 unit from the origin, from the center. Okay. So that helps you fill out pieces of information like, for example, this coordinate over here, because if you also keep in mind that this is overlaid upon the coordinate axes x, y, and you know that even though it's on, a somewhat dramatic scale, if I can get this, come on, autocorrect into a line. Okay, it doesn't want to. All right, try that again. Oops. There we go. Even though it's on a dramatic scale, it's still only 1 unit. So if I have a point that's 1 unit to the right of the origin, it's going to have coordinates of 1, 0. If I have a point that's 1 unit above the origin, there's no horizontal change, so it's going to be 0, 1. The only change is vertical. All right. And we'll fill out, like I said, the rest of the circle based off of that information later. But for now, it's just, if you get that first quadrant, you're in really good shape. All right. So coordinates around the unit circle. You can see that there is symmetry. So once we get a handle on this one, and this one, we'll have everything else. So let me start with the first one. I'm going to drop an altitude. That first triangle is going to have a reference angle of 30 degrees. All right, because remember, the unit circle or any circle starts off to the right at 0 degrees. All right, so that's what we designate zero as the starting angle, 0 degrees. I'm going to write it like there or like that because it's in the triangle, and I don't want people to get confused. It's not a 0-degree angle in that triangle. All right, we'll worry about radians later, but 0 degrees is our start. Now, that's kind of confusing because in the real world, up or north is 0 degrees, and everything is built off of that. So it's kind of like you take your knowledge of the unit circle and pretend that north is to the right. All right. It's aggravating, but when we get into the robot activities, you'll see in terms of headings and directions that everything is going to start off with 0 being 12 o'clock, and then based off of that information, we designate other angles. So it's a right triangle. We have 30 degrees. The other angle must be 60 degrees. All right. So if you know your 30, 60, 90 relationships, you can populate the missing sides here. But you could also use a calculator. You could use just, prior knowledge and stuff like that. But at least for the first couple of computations, I'll do it using the 30, 60, 90 relationships. All right. So just kind of off on the side here, I'm going to sketch it out. A 30, 60, 90 right triangle. So going right back to geometry, or perhaps gap 1. So we have the 3 sides. One side is going to be designated as x. So what I'm going to do is I'm actually going to draw an equilateral triangle, or at least attempt to. All right. If you split an equilateral triangle in half, you get 30, 60, 90 triangles because each of the base angles are going to be 60 degrees. But if you bisect this 60-degree angle, it'll give you a 30-degree angle. All right. So we're going to call the length of one side, we're just going to call that x. All right. In an equilateral triangle, now I'm just bringing back all sorts of geometry knowledge. In an equilateral triangle, the altitude, median, and angle bisector are all the same line, meaning if you drop an altitude, it's going to bisect the base. It's also going to bisect the vertex angle. All right. So that's telling me that I can call this piece here 1/2 x. All right. Then you just need to use the Pythagorean theorem to figure out the missing side. All right. So I can do that, or you could just say, oh, I remember this. that's going to be radical 3 over 2x. All right. So I'll show you the Pythagorean theorem very quickly. All right. So, you know, a squared plus b squared is equal to c squared. All right. So 1/2 x squared plus my unknown b, I'll call this b, squared is equal to, the hypotenuse is always c, so x squared. All right. Simplify, a quarter x squared plus b squared is equal to, I'm going to write it as 1x squared because I'm about to combine terms, so I want to keep things straight in my head. I'll subtract the 1/4 x squared from both sides, and I'll get b squared is equal to, well, $1 minus a quarter is 75 cents. 1 minus a quarter is 3/4. So 3/4 x squared. And when I take the principal square root, all right, the positive square root where I don't care about the plus or minus because we're talking about a geometric figure, this is going to be b is equal to, the square root of 3 is the square root of 3, square root of 4 is 2, and the square root of x squared is x. All right, so that's how you could solve for it if you didn't actually remember it. Actually, let me make this look a little nicer. All right, so if you happen to remember it, that's great, but it's not 100% necessary, as you can see. All right, so if I let x equal 1, all right, to correspond with the radius of the unit circle, then these sides would be 1/2 and radical 3 over 2. All right, so what that gives us is a relationship in any 30, 60, 90 right triangle. If the hypotenuse is equal to 1, the side opposite the 30-degree angle is going to be equal to 1/2. The side opposite the 60-degree angle is going to be equal to radical 3 over 2. All right, so that's all stuff that in theory you've mastered over the last couple of years. But as we know, the last couple of years were kind of weird education-wise. So if that slipped through the cracks, then it's okay. You got your review here. Or more likely, you saw it, you were good at it when you needed to be good at it, but it's been a while, so you forgot. Right? That happens. All right. There's no penalty for forgetting stuff that you don't use all the time. Although my wife seems to think differently. She'll get me at like 2 o'clock in the morning and tell me the schedule for like the next month, and then get mad at me because I forgot it all. Yeah, it is what it is. There's some weird instances that are the exception to the rule. All right, so that's telling me that in this triangle that I constructed on the unit circle, opposite the 30-degree angle is going to be 1/2. Opposite the 60-degree angle is going to be radical 3 over 2. All right, so we now know the dimensions of this triangle. Wonderful. What does that tell us in terms of coordinates? Well, any coordinate in space, all right, in a two-dimensional space, is a horizontal movement followed by a vertical movement. Because x is always the distance, the horizontal distance from the y-axis, and y is always the vertical distance from the x-axis. All right, it's all about movement. We tend to think of coordinates as locations, but those locations are the result of a movement, a translation from the origin horizontally followed by vertically. All right, so what am I doing here? I'm translating to the right radical 3 over 2. And then I'm translating upward 1/2. So now I have my first ordered pair. All right, that corresponds with a 30-degree angle. Because yeah, this is a triangle, but what's actually happening is this ray, if I put an arrow on it, is sweeping through this region to give us this new ray, which could extend out infinitely. It's just in this case it terminates on the circumference of the circle. But that sweeping motion, you know, just think about like if you've ever watched a TV show or a movie where they have the radar screen. You have that line that's sweeping through the circular region, and it shows all the little objects that are there. That's what is happening with the unit circle. You're sweeping through the angle. And so what's really going to end up being the case is that the coordinate 1, 0 is going to sweep through the circumference of the circle and become or move to the coordinate radical 3 over 2 comma 1/2. All right, so it's a different way of thinking about it, but it's a more intuitive and physical approach to things. All right. So the next one. Well, that's going to be a 45-degree reference angle. Now, I don't want to bore you too much. So for this one, I'll just tell you that the relationship for a 45-degree reference angle, and let me just kind of plot it here, 45 degrees, is going to be radical 2 over 2, radical 2 over 2. All right, so instead of radical 3 over 2 and 1/2, the legs of this triangle will compute out to be equal to radical 2 over 2. And because it's 45, 45, 90 a right triangle, the opposite sides are congruent, or the sides opposite those congruent angles are congruent. All right. So the two legs have the same length. All right. So if one of them is radical 2 over 2, so is the other. All right. Now, obviously the diagram's getting a little messy, but we don't really have to draw any more triangles. We could. The next one would be a 60-degree reference angle. But if you just kind of play it out in your mind, a 60-degree reference angle would create a right triangle with a 60-degree angle at the origin. All right, so that would put 60 degrees over here, which would make this vertex angle 30 degrees. So what's going to end up happening is the lengths of the sides are going to swap. All right, so where this one was radical 3 over 2, it's now going to be 1/2. Where this one was 1/2, it's now going to be radical 3 over 2. The angles swap, so the sides associated with those two angles will also swap. All right, so this one becomes 1/2 radical 3 over 2. So we have a quarter of the unit circle accounted for. That's wonderful. All right? I mean, if we took this approach the rest of the way, we'd be here well into tomorrow's class. All right? So that we don't want to do that. We want to take advantage of symmetry. First off, each one of these angles around the unit circle have corresponding congruency. So the angle that's closest to the x-axis, let me get red back involved here, is going to have a reference of 30 degrees. So 30 degrees, 30 degrees. All right? It's just a question of what that translates to in a real movement from the origin. All right? So what we could be having here is an angle that sweeps all the way through, all the way around to go 1/2 of a turn around the circle, which would be 180 degrees. But what I'm saying here is, let's dial that back by 30 degrees. All right, so instead of doing 1/2 turn, 180 degrees, let's short that by 30 degrees. So that would put us at 150. All right, so instead of going 180 degrees, let's short that by 45 degrees. 180 minus 45 is going to be 135. And then instead of, again, going 180 degrees, let's short that by 60 degrees. That would put us at 120. All right? So if you do have experience with shortcuts, I can't get out of my own way sometimes. If you do have experience with the unit circle, you might have learned some shortcuts along the way. All right? One of the shortcuts has to do with the angles. It's always in the pattern of plus 30, plus 15, plus 15, plus 30 all the way around. So if you know it's 30, 15, 15, 30, then you can fill out the unit circle that way also. All right. So the next one, 180, that was the easy one. I'll just put that back in black. Back in black. So 180, go back to red. Increase by 30, you get to 210. Increase by 15, 225. Increase by 30 again, you're at 240. All right. Then we're back to 270, three-quarter turns, 90 times 3. All right. Then plus 30. So that's going to put us at 300. 315. So add 15, add 15 again, 330. And then one full turn would be 360 degrees. All right. Well, like I said, we'll get to radians in a little bit because there's a bunch of different ways to go that route. But if you want to come up with the coordinates, we know that if you reflect over the over the y-axis, you negate the x values. When you reflect a coordinate over the x-axis, you negate the y values. All right, so I'm going to take all of these coordinates here, the ones that we invented with painstaking detail. I'm just going to copy them over here, copy, paste. But I'm going to slap a negative onto the x values. All right, you move to the left, you're from the origin, you're going to have a negative value for the x rather than the y. So I just tuck a little negative there. Then I'm going to take all of these coordinates, bring them down. Yeah, I'll bring that other one there too. Bring them down to the bottom and negate the y's. Oh, I copied a lot of. Okay, that's not going to work. I'll just do it this way. So you negate the corresponding values of y. All right. So same idea here. We'll take these and negate all the y values. All right, so now I have my coordinates. This one would be 0, -1, and this one would be -1, 0. I have all my coordinates. Now I just need the radian measures. All right, so a bunch of different ways you can come up with those. One way would be conversion of all the degree values, but that's not the most user-friendly way to go, all right, because that's a lot of computation. Another way would be to use ratios. So if you know that 30 is 1/6 of 180, and you know 180 is pi radians, and that's because 360 is 2 pi radians. All right, 2 pi radians is a linear distance around the circumference of the circle. So if you didn't know, if you take the unit circle and get one of those bendy rulers and measure around that unit circle, you're going to end up with 6.28 radians, right? 6.28 times the length of the radius. All right. So that's a standard rule. Half of that would be pi, half of 360 is 180. So if I take 180 divided by 6, I get 30. So take the pi and divide it by 6 and you'll get 30. Well, you'll get pi over 6 anyway. You'll get something equivalent to 30. All right. So then I would say, all right, well, how do I get from a 30 to a 60? Multiply by 2. So let's multiply this by 2. All right, 2 pi over 6 becomes pi over 3. And just work off of the previous computations. All right, so I got 90 degrees up here. That's pi over 2. That's easy enough. 120 is double 60. 60 is pi over 3. So double that, 2 pi over 3. 135, I don't have enough information for that yet, but 150 I know is 5 times 30. 30 is pi over 6, so 5 times that, 5 pi over 6. All right, and you can kind of build it from there because 150 times 2 is 300. All right, so double the 5 pi over 6, you get 10 pi over 6, which is 5 pi over 3. 120 doubled is 240, so double 2 pi over 3, you get 4 pi over 3. See, I'm just grabbing information from what I see here. Like I figured out the first one, I'm just building off of that. So 30 multiplied by 7, for example, is 210. So take the value associated with 30, the pi over 6, and multiply it by 7. So 7 pi over 6. All right, 330, that's 11 times 30. So 11 times pi over 6, 11 pi over 6. All right, so we have most of the radians. Now we just got to go the rest of the way. So we know 90 is pi over 2. 45 is half of 90. So half of pi over 2, pi over 4. 135 is 3 times 45. So 3 pi over 4. 4. All right, 225 is actually 5 times pi over 4. And 315 is 7 times pi over 4. All right, but most people don't really truly love that idea of building it that way. You know, it's nice to know in theory. I put the 3 pi over 2 for the 270 because 3 of the pi over 2 is 3 times 90 is 270. Yeah, it still takes a fair amount of work, so you don't want to do that. So we think of different shortcuts or trends or relationships. First off, hopefully you notice that all the denominators for the radian measures are 6, 4, 3 as you work your way out from the x-axis. All right, every one of them. All right. In the first quadrant, the numerator is always pi. So if you know 6, 4, 3, slap a pi on top and you're good. All right. In the second quadrant, this is where it gets a little interesting if you didn't know. You look at the relationship between the numerator and the denominator, you see the numerator has a value that's 1 less than the denominator in every case. All right? So the numerator is the denominator minus 1. All right? So if you notice that relationship, that saves you some time. All right? You'll notice in the third quadrant, the numerator is always the denominator plus 1. The fourth quadrant's a little weird. I mean, it's all weird, but it's kind of borderline, oh, well, that's not really much of a rule. If you double the denominator and subtract 1, you'll get the numerator. So the numerator is 2 times the denominator minus 1 in each case. Take the 3, double it, you get 6, minus 1, you get a 5. All right, 8 minus 1 is 7, and so on. All right, so that one's kind of like, now you're just reaching. You know, that's a fake rule. But that's the unit circle. I mean, it's definitely an acquired taste. If you don't have any experience with this is like, whoa, what just happened? We were so good with the Pascal's triangle yesterday. Now you're throwing this crap at us. Right? It takes a little getting used to, but I can promise you, especially if you're going to be pursuing a career that's going to involve you taking a lot of math classes, this is a gateway to success. All right, knowing the unit circle. All right, I teach almost all the classes that come after this one. I know of what I speak. All right, it's very, very important. So